So in this section, we're going to talk about the empirical and molecular formulas of compounds and how we can calculate those two types of formulas. The first piece of this is what's called the percent composition of a compound, which is a breakdown of the compound's formula by weight into its different elements, and those are expressed as a percentage. So the percent composition of manganese nitrate, MnNO3 first we have to find the mass of each element in the compound. So manganese, nitrogen, and oxygen. Right? And there is one manganese atom in this unit, or this formula unit. And manganese, if you look it up on the periodic table, its mass is 54.938 grams. And nitrogen, there are two, because the 2 outside the parentheses doubles everything inside the parentheses. So it's 2 times 14, which is 28 grams of nitrogen. And then the oxygen, there are actually 6, because it's O3, and then the 2 outside the parentheses doubles that. And so we would do 6 times 16, which is 96 grams. So the total mass of the compound is 178.938. So then what we need to do is take each element's mass in the compound. So not the molar mass from the periodic table, but the actual mass of that element that's in the compound. So these numbers here. And we're going to divide each one of those numbers by the total of 178.938. So I'm just going to put those in here, 178.938, 178.938, and then those get multiplied by 100, which makes them into percents. So times 100, times 100, times 100. And when we do that, we get for manganese, we get 30.7%. For nitrogen, we get 15.6%, and for oxygen we get 53.6%. And if you add those all up, they actually come out to 99.9%, which is slightly off from 100%, which is what you should have. But these three numbers are also slightly rounded, so that accounts for the little discrepancy there. So that tells us that we at least have done some of the calculations right. So the percent composition would be 30% manganese, 15.6% nitrogen, and 53.6% oxygen. So now, once you have the the percent composition, the empirical formula is the smallest whole number ratio of elements in a compound, and we use that, or we do that by finding the percent composition, which in this case will actually be given to you. And if you had 100 grams of the sample, you convert the percents to grams, then you convert the grams to moles, and then you divide each of the number of moles by the lowest number from the group. And that should give you a whole number ratio. So for example, what's the empirical formula of a compound that's 40.5% sulfur and 59.95% oxygen? This is one we did in class, but just to walk through it again as an example, the first step is to take all of the percentages and make them into grams. So we're going to say 40.05 grams of sulfur and 59.95 grams of oxygen. And then step 2 is to convert to moles, and we do that by doing 1 mole over the mass of each element. So for the first one, sulfur has a mass of 32 grams, and oxygen has a mass of 16 grams. So this is step 2. Divide each mass that you got in step 1 by the mass of the element from the periodic table. So what that does is it gives us the number of moles, which is 1.249 moles of sulfur and 3.749 moles of oxygen. So step 3 is to take each of the numbers in that you got from step 2 and divide them by the smaller number, which in this case is the 1.249, and we're going to divide all the numbers on the list by the smallest number. So 1.249 divided by itself, and then 3.749 divided by 1.249. When you do that, you should get hopefully whole numbers. We get 1 for sulfur and 3 for the oxygen, which means that there's 1 sulfur for every 3 oxygens, which means that the empirical formula is SO3. Okay, we use these two numbers, put them into the formula SO3. Okay, another example. A compound that is 81.79% carbon, 6.1% hydrogen, and 12.11% oxygen. So again, step 1, just convert the percentages to grams. 0.79 grams of carbon, 6.10 grams of hydrogen, and 12.11 grams of oxygen. Step 2, convert those to moles. 1 mole of carbon is 12 grams. 1 mole of hydrogen is 1 gram. And 1 mole of oxygen is 16 grams. So you divide those out and you get 6.815 for carbon. You get 6.10 for hydrogen and 0.756 for oxygen. So now in step 3, we're going to take all the numbers we got from step 2, find the smallest number, so that's down here, 0.756, and we divide every number we got from step 2 by the smallest answer, which is 0.756, 0.756, and 0.756. Divide all those out, and you get 3 new numbers, which hopefully are whole numbers. In this case they are. They're really close enough to round. 9 for carbon, 8 for hydrogen, and 1 for oxygen. So we take those numbers for each element and we put them into a formula. So C9H8, and there's the 9, the 8, and then O1. We just don't have to write the 1. Right, so that's the empirical formula for that compound. Now, what about an example where you get to step 3 and it doesn't come out exactly even? We did this example in class as well, but here it is again. 48.64% carbon, 8.16% hydrogen, and 43.2% oxygen. Step 1, convert the percentages to grams. 48.64 grams, 8.16 grams hydrogen, and 43.20 grams of oxygen. Step 2, convert the grams into moles by dividing by the molar mass, which is 12. For carbon, it's 1 gram for hydrogen, and it's 16, oops, that belongs on the bottom, 16 grams. There we go. 16 grams per mole for oxygen. So that gives us 4.05 and 8.16 and 2.7. So step 3, divide each of the numbers from step 2 by the smallest number, which is 2.7. So start with 2.7, 8.16, 2.7, 4.05 divided by 2.7. When you do that, you actually come out with 1.5, 3, and 1. So 1.5 is not a whole number, and it's not close enough that I can round it to a whole number. Okay, it's too far away from being either 1 or 2. If it was 1.1 or if it was 1.9, I would round to the nearest whole number. But when it's in the middle, or if it's say 1.33, I can't round that off. That's too big a difference. But what I can do is if I take all the numbers times 2, I get 3, 6, and 2. Now I have 3 whole numbers that I can use in a formula. So the 3 goes with the carbon, C3, the 6 goes with the hydrogen, and the 2 goes with the oxygen. So that would be the empirical formula of that compound. Alright, so the molecular formula is the actual number of atoms of each element that's in a compound. It's not necessarily the simplest ratio. It might be, it might not be. So in order to figure out the molecular formula, you need the empirical formula. So either you'll be given the empirical formula or you'll have to find it like we just did in the last couple of problems. And then from there, if you're given the molar mass, you can figure out the molecular formula by taking the molar mass of the actual compound, which again would have to be given to you, and you divide it by the mass of the empirical formula, which would be, again, either given to you or you find it. So for this example, CH3 is the empirical formula. And if you looked at that, carbon is 12 and hydrogen is 3. So that's a mass of 15 grams. And the problem would tell you that the actual formula is 30 grams, for example. So you take the molar mass, divide it by the empirical mass, and you get the answer of 2, which means that the actual formula is twice as big as the molecular formula. So you multiply the two numbers, C1H3 by 2, and you get C2H6. Let's do an example here. So in this case, we have to, we're given the percent composition, we have to find the empirical formula, and then the molecular formula because they give us the molar mass. So first we have to go through the steps of turning the percent composition into an empirical formula. Step 1, convert the percents to grams, so 74, 8.65, and 17.35. So the first one is carbon, which is 1 mole for 12 grams. Hydrogen, 1 mole, 1 gram. And the last one's actually nitrogen, not oxygen, which has a mass of 14 grams. So we do those out. Step 2, right, that's step 2. And we get 6.166, and then we get 8.65, and we get 1.239. So step 3, take the answers from step 2 and divide them all by the smallest number, which is 1.239, 1.239, and 1.239, and you get 5, 7, and 1. So that's step 4. So the empirical formula is C5H7N1. That's the first part of this problem. Find the empirical formula. Okay, determine the empirical formula. That part's done. But we also need to find the molecular formula. And they tell us that the molecular mass, or molar mass, is 162.26. So that goes on the top, 162.26 grams. Now for down here, we need to find the mass of that empirical formula. So it's C5, which means 5 carbons, 5 times 12, H7, 7 times 1, and 1 nitrogen times 14. So that's 60, and 7, and 14, which is 81 grams. So when we do 162 divided by 81, we get 2, which means that the molecular formula is twice as big as the empirical formula. So the molecular formula, make some room back over here. The molecular formula is taking all the numbers from the empirical formula and doubling them. So down here we're going to have C10, H14, and N2. That is the molecular formula. Okay, so we have two parts of the question, the empirical formula, which is here, and the molecular formula, which is down here. Okay, so one more problem on this. Okay, we've got the percentages, so we're going to have to do the empirical formula first. 40.68 grams of carbon, 5.08 grams of hydrogen, and 54.24 grams of oxygen. So that's step 2, is divide them each by their molar mass. And we get 3.39 for carbon. We get 5.08 for hydrogen. And we actually get 3.39 again down here for oxygen. So step 3, there's actually two numbers that are both the smaller number. So we're going to divide everything by 3.39. 3.39. And we get 1, we get 1.5, and we get 1. So again, we've got a situation where we don't have a round number in this 1.5 in the middle for hydrogen. So I'm going to take all the numbers and multiply by 2. So we end up with 2, 3, and 2. So the empirical formula is C2H3O2. Okay, so that's the first part, the empirical formula. They tell us that the molar mass of the compound is 118.1. So now we need to find the mass of the empirical formula. So it is 2 carbons, which is 2 times 12, or 24. 3 hydrogens, which is 3 grams. And 2 oxygens times 16 is 32. So that gives us a total mass for the empirical formula of 59 grams. So 118 divided by 59 is 2 again. So what we do here is that means that the molecular formula is 2 times the empirical formula, or C4H6O4. So that is the second part of the problem, the molecular formula.